Welcome, everybody. I'm Drew Jones. I'm the co-founder, executive director of Climate Interactive, and we're thrilled that you're here for the webinar using En-ROADS to simulate carbon dioxide removal. I'm here with Ava De Leon. She's going to be in Q&A answering a lot of your questions. We're going to be using the simulator to dig into this question of carbon dioxide removal. But first, we want to know where you're coming from. It's always so helpful. So please open another browser window in the top corner, and I bet you look into chat, you can see that Ava has posted polev.com in the spot. Open up a browser window and let us know where you are. Put a pin in the spot. I think there's someone in Boston and maybe Scandinavia and Asia and Seattle. Always so helpful to see where you're coming from. California, Pacific Northwest. Maybe people are writing into chat as well, where you're coming from. We'll look into that. Minnesota, Santa Cruz, Turkey. Oh, we're welcoming Skook Jones from our team who built much of this sector. Argentina, Asia, see that person in Turkey and Italy. Thrilled to see so many folks here today. If you're just joining us, please open up another browser window. Go to the link at the top, polev.com, and let us know where you're coming from. Love to see it. And we'll be using the polling more in this webinar, so this is a good way to get it set up. We're going to need you to share it. Welcome. Please do the poll. People are coming from Sierra Leone, Brazil, Rhode Island, USA, Eugene, Oregon, Benin, South Korea, Chicago. Good to see folks coming from all around the world. If you're just joining, I'm Andrew Jones. You can call me Drew. I am the co-founder and executive director of Climate Interactive. We are a US-based nonprofit climate tech company. And what we see in the world is that top decision makers are having to make too many decisions based on ideology, intuition, and pressures, as opposed to grounded in the best available science. So we give tools to you and to others to get to those top decision makers, to help them actually change their minds about what is high leverage, what is low leverage when it comes to addressing climate change. That's the promise of these tools, such as En-ROADS, the simulator we're going to be working with today. The simulator we're going to use to analyze carbon dioxide removal. We're really curious on the topic. What is it about this topic that makes you curious? Why are you here? What inspired you to join? Please go to this second poll question. This will give us a sense of what domain you're coming from, what are the particular nuances of this question, what are you curious about? You need to know. You do need to know. Absolutely, you need to know. I agree. What else inspired you to come here today? What is the efficacy of various carbon dioxide removal? How much carbon could it remove? Better understand its effects. Its direct effects, other effects as well. Science, synthesis, and translation for responsible decision making. Are we making decisions that actually solve the problem? Excellent reasons. Curious of other reasons. Better understand the effects of carbon removal. Great. So please go to the polls if you're just joining. You can see the link at the top of how you get to them. We'd love to see what your answer is. That this is such a valuable tool, En-ROADS, for climate change remediation. Oh, not addressed very much. Oh, that the tool could be carbon dioxide removal is a valuable tool. It's an assignment for work, but generally interested in En-ROADS as a teaching tool. Biochar, we'll look at that for carbon dioxide removal. Enhanced recovery. I just love seeing the model and what new things Drew can show us. It helps you improve your presentations. The massive scale up of CDR that IPCC says is required is impossible to show. Are there multiple examples? This is critical knowledge. Time is running out. Cost versus effectiveness. What is the cost of CO2 removal relative to other carbon reduction strategies? You like to ID the best graphs to share in En-ROADS based on the various decisions. Can it get us to under 2 degrees Celsius? More information about how En-ROADS could be used to help with carbon removal. Are there negative side effects of any of these techniques? Looking for better ways to help or contribute. It's a growing industry. How could it be applied in the voluntary market? Great. Love it. You are in the right places, my friends. Okay, here's us. We work closely with MIT, the Sloan School of Management, the Climate Pathways Project. And boy, this is so in the news. So this morning, there was a new article and it came up in my email feed. And Ava, could you post it? It's interesting, the framing on the email feed. It's becoming increasingly apparent the world is going to need carbon removal to meet ambitious goals. Companies are doing things. Then you click through, and over on the right is a different framing. So it's kind of like, oh, they're spending a lot of money. We need it. And over on the right, when you click through, big bets on speculative carbon capture tech ignore today's solution. So it starts setting up this interplay between the possibility of carbon dioxide removal and what's really needed to meet goals. Investors and buyers are backing futuristic carbon technologies rather than ones working at scale now. So a little bit of those dynamics. This is just a bit in the news today. So we're talking now about the motivation. I'm going to show you a lot about results, but also summarize some of the mindset shifts that we encourage as you become better systems thinkers about CDR. Here are the 6 methods in En-ROADS we're going to look at in a minute. Marine isn't on this list. We're hoping to raise some money to add it. But here they are with some little diagrams, and we're going to simulate them in a minute. So trees, natural carbon removal. If we grow afforestation, more trees in new areas. Reforestation, places where we already chop down trees, could they grow back? And then just existing forests, not chopping them down or harvesting them as intensively. Natural carbon removal. BECCS is bioenergy, where we're processing or burning biomass, trees or plants in some way or waste. And some goes into the atmosphere, some gets captured and put underground. Could that be a removal technique? Biochar, again, trees, this kind of burning process creates biochar, can be spread on land. Some gets removed, some gets released. Ag soil carbon, if we don't till the soil as much and we use advanced techniques, more can stay underground. Of course, until you till it, and then you can lose the carbon dioxide, but more could be stored. Enhanced mineralization, crushing up rocks. It takes some energy. Spread the rocks on the land. The rocks absorb carbon. Do it every year or every few years. You have to keep applying it in order for that to work. And then the final one that we will be digging into the most, direct air capture. Very energy intensive, pulls it from the atmosphere, not from the end of a smokestack, the flue gas of a coal-fired power plant or a gas-fired power plant. Pull it straight from the 420 parts per million that is in front of your face right now. Capture it, put it underground into saline aquifers primarily. We'll be looking the most at that one. So my first question about all of those, what are you the most interested in? Of these, which approaches are you interested in simulating. I didn't say which do you like, but we're gonna run some scenarios, and we've got six. We've got six. I already told you what I'm gonna do a bit because Skook and team have just come up with more modeling on one of them, but and biochar, mineralization, and wow, many votes. Great to see where your votes are landing. Um, keep on voting. Keep on voting. Okay. It's across the board right now. It's ag soil sequestration, direct air capture. All right. We're going to do this first at the simplest, most basic level. So think of this as first kind of their most basic way of engaging with En-ROADS on this topic. And then we're really going to dig in. And as you know, with new users to this, there are two modes. If you go 100 meters into the MIT Museum, you're going to see this screen sitting there where if you have a 3-minute interaction at the MIT Museum, you can just hit some things and see what changes without digging in deeper. But underneath the hood, you're going to be able to look at, or in this case with bioenergy under here, what are the feedstocks, and are you going to encourage carbon capture and storage for bioenergy or not? That's the advanced view. So first on the most basic view, and then we're going to go advanced. So if you have 20 minutes and you're showing En-ROADS, here's what you're going to do. You're going to say, here's a future, a somewhat conservative, not ambitious climate action future, but we think it is a reasonable assessment of where things are headed. We're headed towards 3.3 degrees. You could show many of the impacts that are out there that people care about other than temperature. We care about deaths from extreme heat. We care about health, malaria, and dengue. How can we prevent the extinction risk of endemic species and other things like this? That's the challenge, given where things are going for where we get our energy. And we'll dig into that more later, but just to say, this is a future with coal and oil and gas and wind and solar, but also methane emissions and others that give us this pollution. This is the pollution that is causing the warming of all the way up to 3.3 degrees. If someone says, yes, but can't carbon dioxide removal help? I just read an article, and this article that says that maybe if we can learn how to capture the carbon, then we don't have to worry about how difficult it is to reduce those emissions. So here is that quote that that person read. And they said, an oil CEO answered the questions. Vicky Holub is the CEO of Occidental Petroleum. I care about our planet, she said in the New York Times. I care about people that are impacted by climate change. And we should continue producing and burning oil and gas until every molecule has been extracted from below the ground. When I asked, this is the interviewer, when the world should stop using it, she replied, that's when we run out of oil and gas. How do you reconcile that two? She said, one day it will be possible to use oil and gas without producing planet warming emissions. Occidental is investing in direct air capture, which is pulling carbon out of the atmosphere. If we can deal with the emissions, we can continue to produce oil and gas. So someone says that. How do we think about this potential? The simplest way in En-ROADS to think about this question is to do a simple test. And the simple test is, what if we get carbon dioxide removal? And I'm going to test it not just in one area. She mentioned she's investing in direct air capture, but pretty much across the board, like it works in multiple areas. To do that, you're going to click here on these graphs. These are our 12 favorite graphs, CO2 removals. And over here, you can see you're going to see different types of carbon dioxide removal. In the top right of the sliders, here are nature-based. You can see the details underneath, technological. And instead of the status quo, you could start imagining that growing into the future, we're going to have some more low growth. And here it's given our success to implement policies around the world, maybe medium growth would be ambitious. So medium growth in nature-based solutions gets us removals, afforestation and reforestation in green, ag soil carbon, and biochar. Each of them, great success. And then technological from a little bit to a little bit more. And here we are with direct air capture, and we're adding mineralization to the medium level. So we're getting some and really a good bit. Why is it helping? I'm just going to undo it. The basic premise of this, of course, is you can think of carbon in the atmosphere, all of the stuff that's trapping heat as a bathtub. And the red line on the left is what's flowing into the bathtub. This is emissions in red. You can see it's up here today around 42 gigatons a year flowing into the bathtub. What's going out of the bathtub into oceans and into plants is, and into soils is the blue line of removals. The premise here is that maybe we can push the blue line up, not just bring the emissions down, push the removals up. It's like a bathtub with a big drain, flows out. So I'm going to redo what we just did and redo it, I think, and go back to those two actions and watch that. Do you see the blue line? Actually, let me do it. I'm going to reset it. If we go, yeah, there it is. You see that change. There it is. We're boosting the removals. Now, noticing the removals don't double. They go up modestly. And what is that doing? That is bringing overall net pollution down and temperature down. How much? In this case, about 0.1 degree. What are we saying? An ambitious diffusion of carbon dioxide removal across multiple approaches would lead to that about 0.1 degree drop in temperature because of the boost of removals and getting a little bit less CO2 concentrated in the atmosphere. But the key premise here and the key idea is that it's not compensating at all for fossil fuel emissions. So back to Vicki Hullab, she said, maybe we could or we need to have it compensate for CO2 emissions from fossil fuels. And you can just see the scale and understand why that's the case when you look at the amount. We're getting up by 2060 to 7 gigatons. Here we are in 2060, and it's emitting 38. So these two things are not compensating from each other, even, well, certainly not in the near term. They're not. It's taking a long time. That's what, 50 years to get up to these higher levels, whereas we're emitting carbon from fossil fuels for many years in the interim. So the short answer is it's not a substitute for mitigation. And the second question, though, I really want to address with it, if it's not a substitute, uh, is it a priority then? Because well, that's 0.1 degree. How does it fit into the suite of possibilities and the needs of the world today? And I want to emphasize a second question. So clearly not a substitute. So we get to say, no, Vicki Hollub, what you're talking about would be nice if it could compensate for the emissions, but it just seems like as we simulated it in En-ROADS, it can't. However, is it still a priority? Is it something that we should really focus on? The IPCC said 2018, it would be needed to get to 1.5. How much should the world say this is worth conversations? Should Bloomberg be sending an email about it? Is it a top priority? When we answer a question like that at En-ROADS, we are as serious as a heart attack about the urgency today. The urgency in climate change today and a focus on priorities is this. Here's 1860. Here's 2100. This is the temperature as observed in those little dots. And then here, this projection in blue. This is from our colleague Zeke Housefather. You see these little dots here? There's 1.5. Here are the last 2 years. See those little dots? And I'm going to make them bigger now. They are just above recently 1.5 and just below it. We're on a trajectory above where we thought we were in this blue line. It's warmer for reasons. The Earth doesn't seem to be absorbing as much carbon out of the atmosphere. There are other things like El Nino, but we're warmer than we expected to see. We've been in this work for 30 years, we expected to start seeing carbon dioxide concentration leveling out. This is the stuff that is trapping heat, atmospheric CO2, measured out in Hawaii. But what we've seen over these last 20 years is not a balancing out, but those emissions, the concentrations have been going up. We also had expected to see coal, oil, and gas emissions peak and start to fall by this point. However, instead, we've seen it going up and up and up. So the belief that perhaps mitigation has been handled, that we are really on track to reduce emissions, we don't have as much confidence that that is the case. Therefore, this question of priorities, what are the top priorities as we all try to address this problem? And note, not what could be done or what are industries that are going to grow, or what is the difference between getting to 1.6 degrees or 1.5. But I'm talking about the difference between 3.3 and 3, or 3 and 2.5, or 2.5 and 2. What are the priorities to get us there? That's what I really want us to focus on. You saw my first tests, and I want to now dig into why some of those results are so modest and why we're likely to see much lower uh, lower results from things like direct air capture. And I am going to switch over there to talk about much lower results. Here's some of the promise of what has been sold to us and really why it sounds like it should be a priority. Boston Consulting Group. Direct air capture belongs in every company's net zero plans. It has the potential to remove 5 to 40 gigatons. So remember those numbers, 5 to 40. And the cost coming down to a manageable $200 per ton. So hold those numbers. 5 to 40 is the scale. Why is it growing so big? Because it's so inexpensive. It's actually happening to some degree now. Actually, there are only 5 plants around the world that are of non-just pilot size. There's going to be one that's being built in Texas right now, which is about 500,000 tons per year. It could scale to be 1 million tons. That's about the size. So think of them around 1 million tons per year. That's how much this one in Texas could scale to. What do they look like? Like these big fans. They pull carbon through them, and then they grab the carbon and they pipe it and shove it underground. Here's one in Louisiana. So let's go and test it in En-ROADS. And again, remember, we're aiming for 5 to 40. We really hope that the scale is that, and that the price could get all the way down to a manageable, as they said, $200 a ton. Where is it today? Here is the graph. Scoop, you built this. Estimated the cost today at $650 a ton. That's what it is as the start in En-ROADS. Some history on this. Simon Evans wrote a nice tweet that laid this out pretty well. 2017 said it cost $600 a ton, aiming for 100 by around now. In 2021, it said 200 to 300. But in 2023, 2 years ago, it said $1,000 a ton, then 400 to 600 by 2030, and then 100 to 300. Then prices are changing a good bit, and the estimates, we say $650 a ton. If you don't like that number, like many others in En-ROADS, you can go here under, and I'll do this more slowly. I'm starting, the adrenaline hits me. Go to simulation, go to assumptions. Under assumptions, scroll down, 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 direct air capture and storage. Important assumptions about how big it's going to grow, how the costs work, what the progress ratio is. We'll get to that in a minute. And the initial cost. Where do we get assumptions like this? Here are our sources. We partly want to trick you into go read reports. So go click on it. You can read the report that said we think it's about $650 a ton. There it is, 650. Watch the line in the top right. It could be higher, it could be lower. Simulate what the implications would be. So there it is, 650. We're going to simulate it under technological carbon removal in the top right. Click the dots. Use the detailed settings. Like the basic one, it just says, okay, we're going to get a lot of it. That's moving all of them. Don't do that. Get specific. Detailed settings. And what we're going to do is subsidize it. And this isn't a subsidy that you just pay for a little while. You have to just always pay for direct air capture. It isn't like wind and solar or nuclear or something that you could subsidize and then it makes its own product and then it can use the revenue from the product to keep reinvesting. Therefore, the subsidy can be temporary. It has to be paid for. It's like, think of it as trash removal for a city. You're just constantly just cleaning up. And so it is a steady cost. How much are you willing to pay per ton? And we can calculate the total money. But for here, it's direct air capture, subsidy, and let's just say, all right, we'll pay the price. We're going to spend that 650. Run your mental model. Run your mental model. How much do you think we'll get? The best thing to look at is sources of anthropogenic removals. Well, we already got it. Wait, I'm going to go back here. And 650, run your mental model. And boom, there it is. What do we see? The removals are going up by 2060, 0.52. There's some mysteries here. I want you to notice that was 0.52 in 2060, but actually captured is 0.72. 0.52 is actually net removed, and 0.72 was actually captured. There's a difference between the two. Why would there be, why would there be a difference between what you actually capture and what you can really count as net removed? Anybody, so I'm doing another poll. Someone knows this. Captured is what is pulled in the machine, piped, shoved underground. And the net is when you're takes energy to capture it. That's it. It takes energy to capture it. And what does it take to make energy? You have to burn energy. You have to burn coal and gas to capture the carbon. You have to burn coal and gas to capture the carbon. Now, some are saying, and some people do the math in a somewhat, well, we don't think it's an accurate way. You shouldn't say, assume that you're using all the wind and solar, only wind and solar to produce your energy for the direct air capture. The best summary of the statistics with that math is from Joe Rome of University of Pennsylvania. Fantastic study. Ava, can you post the Joe Rome study? And there he has a statistic. It takes like all of the United States wind and solar to power the direct air capture if we wanted this much removals. It's a large amount. No, don't think of it as you're going to take all that renewables that are crowding out coal and gas and cutting emissions that way, pulling it out and using it to run direct air capture. The opportunity cost is very high of that. That's not the way to think of it. Think of it that you have to burn some coal, you have to burn some gas, you have to use some wind and some solar, probably some nuclear, but the overall grid provides the electricity. That's why there are a little bit of emissions, some removals, but that 0.72 goes down to actually 0.52. Okay, I'm going to go back here. 0.52 is what you get. Not, remember those numbers, 50, no, 5 to 40 is what the others were estimating. And this number of 0.52 or 0.72, I just want to kind of right size it with your understanding um, of others' estimates. Janet Tchaikovsky on our team did a great look at this amazing table she made. This is our own table. And this is how we have to calibrate and test our model, which is all the other groups' estimate of how much we're going to see. Remember I said 0.72 captured, removed 0.52 by 2060. These are 2050 estimates. BP, current trajectory expects zero. Net zero scenario has 1 gigaton. Remember again, we were 0.72 captured. Equinor, the oil company in Norway, said zero point 0.6. Another scenario, 0. Shell Horizon has some scenarios. So other oil company, 0.3, zero point 0.8. Rhodium said 0.2. Oops. And International Energy Agency, the most ambitious was 0.8. And then the IPCC scenario said almost zero by 2100, by 2050. I'm sorry, I did it again. Then there's this outlier. This 5 to 40 came from this estimate from this researcher, Sabine Fuss, who said maybe up to 40. That's where these numbers come from. But just to anchor, this is where we're sitting in the range of what others seem to be showing for what's possible. But then the question is why? Why are we getting so little of this? The main reason is it's incredibly expensive and not getting cheaper. Look over on the right. This is not the curve. I see my colleague Scoop Jones, who did a lot of the modeling here. And the first time I saw this result, I was waiting to see what, that steep drop, like it's the cost of mobile phones or air conditioners, or at least wind and solar. Why isn't it dropping steeply? Remember those numbers we heard before? People were saying by 2030 it was going to be $500 a ton or $300 a ton, or that first study that said $200 a ton is what we should expect. It's only getting down by 2080 to $500 a ton in this scenario. What is going on? Well, the way that technologies get cheap by their own forces, not with subsidies, but as technologies develop and you get the benefit of learning, is through a powerful reinforcing loop. This is what brought wind and solar down to be so incredibly inexpensive. 90% drop. Cost goes down. Production goes up. Cumulative experience goes up. The efficiencies in production, you've done it a lot. You get the kinks out of the production system. Field experience, you know how to sell them, site them, build them out in the world. Public acceptance. I don't mind having one of these in my state, in my backyard, in my neighborhood. I don't mind the pipelines. Building public acceptance over time. Research and development, major breakthroughs in the technology. That brings the cost down more. This is a reinforcing positive feedback loop that is driven by or governed by, in our model, what's called the progress ratio. The progress ratio says Every doubling of cumulative installed capacity of direct air capture, when you go from 100, well, 1 million tons a year to 200 million, and we're not even there yet, to 400 million, to 800 million, to 16, 32, 64, 128, growing and growing like that. Every time you double cumulative installed capacity, it brings the cost down a certain amount. Oh, and I'll show you when it does that through this reinforcing loop, the dream of it is that your subsidy is just like pushing a snowball off the top of a hill, and then it's going to self-generate its own cost drop over time. Now, what we're learning about what is that progress ratio is that when we went and researched it, Malhotra et al. Found that CCS, carbon capture and storage, is up here. Do you see where it says CCS right here? It's in this area up here, in this 2x2 matrix or this 9-part matrix. It's very high in degree of design complexity. It's very complex in its design, and it's kind of medium in the need for customization. Each one is a new application. Therefore, the progress ratio is not generous. You don't bring costs down a lot with every doubling. Bioenergy carbon capture and storage is in the top right. It's even worse. What is low in customization and degree in design complexity is solar PV. That is why in the model, what we've seen over time in the past has been, excuse me, the cost of solar has dropped since 1990 radically as we have more and more experience. However, the cost of direct air capture is falling only slowly because direct air capture's progress ratio is 0.9. You get a 10% drop with every doubling of cumulative installed capacity. Now, someone could argue, Drew, you are not giving it enough of a optimistic framing. Skook, you sandbag this technology. It should be 0.85. Now watch as I change it lower to 0.82. You see that? 0.82. And over here, I should pull up removals and see how much more do we get. So I'll do it again. If it's steeper, we get a little more growth. But it's revealing the second problem. It's not just a not very generous progress ratio. You're not getting enough built in order to double cumulative installed capacity and double it again and again. It's not getting going such that you're getting enough benefit. We're not building enough. Now, then you might say, well, wait, you're not building enough. Are you building very much? Well, actually, here by 2060, 57, actually, I look at the capture. The total captured is 0.78, 780 million tons a year. 780. Do you remember what I told you was the average size? That one in Texas was going to get up to 1 million. So that is 780 plants built around the world over the next 50-ish years. That's a lot of these plants. What is that, like 25 a year or so? So this is a lot being built. The key here is a lot are being built and it's not getting cheap. So our estimate of the cost drop is that it won't get cheaper, so we will not actually get that many. So overall, extremely expensive, not likely to get cheaper, and much too inefficient to make a significant dent in overall warming. Because I showed you how much we just captured, and what did that do? That brought the temperature down a almost negligible amount, not likely to be a significant priority. Now, when we get to much lower temperatures, maybe this is one of the things that drops a little more. Now, again, you may say, hey, this could get a lot bigger. And in En-ROADS, if you really want to assume some other magic that we don't see happening, like this could be a much bigger industry, you think, we do allow you to test that because we're curious. So I'm going to bring the progress ratio back to a reasonable point and then see, well, if it does get a good bigger, if it could get to 2 or to 3 or to 4, what would it actually do? Now, mind you, we still have the energy penalty. Temperature comes down a little bit, but it is not enough to be a significant priority. Too expensive, not getting cheaper, too efficient, and too delayed to make a big dent, and unlikely to compensate for fossil fuel emissions. Therefore, not a top priority when we think of all the things that really badly need to be done to address climate change. Okay, that's been quite a run through a lot of the things that a lot of our conclusions. When you're digging into it, you may have some other curiosities and you may say, well, how about storage? What do we know about what it takes to actually build the pipelines? And there are the trillion tons of cubic meters, excuse me, trillion cubic meters that would be needed in pipelines relative to the natural gas capacity, but also the fact that how much does it cost? I showed you the energy used is significant. There it is in gigatons. But when it comes to money, I think down here I can look at total annual cost. And I think I've made it much too high. I'm even going to go back. Let's go back to a more reasonable assumption. Remember where we were before, and we said, what if we had this amount in the scenario I showed you, which was like 0.72 removed? By 2060, we'd be spending $380 billion a year to remove this on kind of like trash collection. This is what it would cost. This is largely funded by the voluntary offset market. And just think for a second, what do you think this would take 360, 370 billion tons? What is the size of the offset market? In 2024, it was 1.4 billion. In 2022, it was 1.7. So this is what, 260 times as much as being spent to offset carbon today would be dedicated here to spending all the money to do that. These are some of the reasons that we don't think it's going to happen and therefore shouldn't be counted on as a priority or as one of our solutions, and really isn't worthy of the level of attention, conversation, and focus it's getting. Let's get back to some of the core work of not burning coal, oil, and gas, reducing methane, F-gases, nitrous oxide, and protecting forests. Okay, let's pause for a second. Those are the priorities we see. That last one, though, let's explore a little bit about forests. And I just want to see if you agree with me where you sit on this one, carbon dioxide. So on forests, reducing deforestation and reducing forest degradation is carbon dioxide removal. This is not, we're saying not chopping down trees, not harvesting as intensively. Do we agree or disagree that it's CDR? It's carbon dioxide removal. Is reducing deforestation and forest degradation carbon removal? Are we grabbing carbon out of the atmosphere and putting it underground? It's interesting. We have quite a polarity here of some different views. Strongly disagree, somewhat disagree, some groups, somewhat agree, strongly agree. Okay, I love it. We have disagreement. Let's go simulate it in En-ROADS. I'm going to undo this. Here we are. Going to go back. I'm going to pull up deforestation. It's under land, forest, and food. Deforestation. And over on the right, I'm going to pull up removals, CO2 removals from land. Gigatons a year pulled out of the atmosphere from land. Okay. Or by land. Okay. Deforestation, CO2 removals every year. And here I go. Um, well, let me just do the basics first of the emissions. I'll just show you. Here's how we think of uh, overall. Do I have gross emissions from land use? Let me see. When we think of cutting deforestation, no, let's just stick with that one. We think of it as reducing emissions. Here comes deforestation cuts. I'm going to reduce it a lot. Look in the top, in the bottom left, in the top left, deforestation, we reduce it significantly. Emissions come down. We're not burning trees in order to make agricultural land. This is a lot in Brazil and Indonesia. This reduces emissions. But let's go and look to removals. What happens to removals? We'll go back, and here we're simulating it, and I'm going to do it again. Reduce deforestation and land degradation. Look at removals goes up. Here in 2070, it goes from 15.8 to 17.25. What is that? 1.5 gigatons a year. 1.5 gigatons. That's double what we got from direct air capture. Double what we got from direct air capture by not chopping down trees and harvesting them as intensively. Why? We're letting trees grow older. Older trees remove more carbon. So even without planting new trees, we're just allowing the trees that we have to get to a stage of their life where they're able to remove more carbon from the atmosphere. Million hectares does of trees more than 100 doesn't follow the dotted line. It follows that solid line. We have a boost to overall removal. So reducing deforestation is natural, the most natural, I would argue, carbon dioxide removal. Also, just give a prop to like where the real removals is also happening. Oceans do it naturally anyways. We'll explore later if we can find the funding, whether that can be enhanced, but that's where a lot of the heavy lifting goes. Okay, so we've looked at two types, direct air capture. We've looked at this natural form of removals. And maybe while I'm just talking about these other removals, I'll pull up these removals from land and we can explore, we can cut deforestation, but we also can explore in here land for afforestation and reforestation. I'm going to increase it here to a moderate level, and we can see that that is another thing that somewhat boosts, not significantly boosts, but increases removals. You can change how much that happens here by scrolling down to afforestation and reforestation. How much land are you going to dedicate to this? I'm going to put in here land for carbon dioxide removal. This is the area of India. I just dedicated a lot of land. It could be more, it could be less. This is an equity challenge. Who lives on this land? Who is growing food and land that you want to turn into forests? What does that do to food prices for people? Equity challenges of using that kind of land. So be careful, but it could be a contributor to boosting removals. Some of the others, bioenergy, carbon capture and storage. Here we have the removals from afforestation and reforestation. What is that? Well, carbon capture and storage can be applied to the three major types of bioenergy. From waste, it's being done. Biofuels, there's ADM has a big plant on ethanol, and there's a big wood chip bioenergy plant that's being planned in the UK. Three different types. What if we subsidized? No, we don't need to do that. Uh, Bioenergy on top of it. I'm going to go down here to bioenergy, carbon capture and storage. You can pull up CO2 emissions and then emitted from bioenergy. Already in this scenario, I'm going to undo where we were. Here is CO2 emissions from bioenergy. It is not carbon removal. It is not carbon neutral. The emissions would be going up over time if we had more bioenergy. If we subsidize it a good bit, perhaps we could capture some. But our estimates is that it's expensive enough and the price isn't coming down steep enough that it would be a relatively small amount. You can see the little blue area is how much is being captured by carbon capture and storage. That is, what is this scale? Is perhaps half a 0.22 or below 1 gigaton a year. Note how ambitious dreams were by some, at least some modelers, who were estimating really, really off the charts estimates. I looked back into history and found that this is what, back in 2018, modelers were including in models to imagine how they could get to 1.5 degrees and said, not we know how to do this, or we can really see an industry growing to do this, but if it were possible, and if we had 10 gigatons a year, 20 gigatons a year, as opposed to what our calculation of a more likely estimate, which is closer to below one. You see way down here where I'm pointing? That's where we think it is more likely to go. And we gathered some other estimates as well. And this is supported by, you can see here, British Petroleum 0.07, British Petroleum 1.1. The more practical estimates are much, much lower. And it really just calls into question where we were as a modeling community that we would put into models 10 or 20 gigatons a year as we did before. Okay, so we've added some bioenergy to this scenario, and then we can look at some of the others that do exist and could be considered. I'm going to pull up these removals. Okay. What are the others? We showed them briefly at the start. What if we had a modest amount of afforestation and reforestation? Possibilities for not tilling soil as much, best practices. Watch the yellow area grow. This is another speculative one. It doesn't exist at scale now. Maybe if we got 30% of that potential. Biochar is another one. Perhaps this is now, we're kind of imagining what could be major in the future if we had significant growth there. And then over in the technological areas, a more reasonable amount of subsidies could get us a little bit of direct air capture. And then I told you about crushing up rocks. So in a scenario like this, with ambitious, large amount of direct air capture, biochar, planting trees, or ag soil carbon, we might see, and it would be a contribution to see about that amount of net removals. That amount of that kind of drop in overall emissions. So this leads us back to my priorities discussion. So absent significant reductions in coal, oil, and gas, methane, nitrous oxide, F-gases, and protection of forests in the next 10, 20, 30 years. Those are the priorities. Absent that, this is not a priority and at best a distraction to spend too much time imagining what could possibly help out in the 2050s and the 2060s. We have to be fierce as we direct global strategy in business and government towards the highest leverage, highest priority actions. And this right now, this area is falling low on those priorities. Now, mind you, if you have a, a direct air capture facility that you can run, if you have a corporation where there is a budget and you must spend it on offsets, it and it could go to carbon removal. Like every pound, every any bit of carbon dioxide that gets removed from the atmosphere helps. This world is better for having removed some. So if you have areas to plant trees, well, trees should be planted anyways, but actions probably should not be stopped, but they cannot draw our attention away from the top priorities. And you know what those are. Here in En-ROADS, we can simulate them quickly in this kind of scenario. And here's where it could help. I'll just do this really quickly. You know what it takes if we encourage renewables, remove subsidies on coal, oil, and gas, electrify to use the zero carbon energy, have energy efficiency, reduce our demand for energy overall, cut methane, cut F gases and nitrous oxide through best practices and changes in behavior, through deforestation cuts. If we do these things and put direct pressure on burning coal, oil, and gas, if we get to that 1.9 degrees, if we do the priorities, direct ourselves with courage towards the things that we know are so hard to make happen, but we know they need to happen. And just because it's hard to do doesn't mean we should go do the stuff that the market seems to possibly be driving, but we know isn't going to help us. Now, the IPCC said, CC, we may need this. When they said that, what they mean is, at this point, if we're on track to make that happen, if we're on track to make CO2 emissions from fossil fuels fall like that, if we are on track to make emissions from methane fall like that, doing the things that we know create the pollution, if we're on track and we can say, you know what, we're making this happen. We've handled the priorities. Okay, we've handled the priorities. Let's get busy here, folks. There's some things that could get us 1.8. There's some things that could get us 1.7 here. Okay? Maybe 1.6. Maybe 1.6. That could possibly supplement what needs to happen as priorities. Did you see that? It could make the difference between a 1.9 and 1.8, 1.9 and 1.7, getting us to well below degrees, and I would love 1.5. But the evidence right now is that we're not on track to handle the priorities and the basics, the pollution that is causing the problems. That is why our analysis is suggesting that we should focus on these priorities and de-emphasize other complementary things until we know that we're much more on track. Keeping focused on that top priority will be challenging. It's not going to be easy. It's going to be worth it. All right, I'm going to stick around. It is an hour. It took an hour to go through all this. Props to the amazing team that built this. I see Skook and Lori and Ava and Laura, and others who are out there who built all this amazing work. I'm going to stick around. This is the first time we really shared that thesis. So I'm interested in answering your questions. I hope you've been writing them in Q&A. So I will stick around after this call. But now it's the top of the hour, and I want to thank you for your attention. And I want to invite you to, well, if you're still listening, Use the theory of change that we have. The most powerful thing that we have is not that message that you just heard. The most powerful thing we have is this open source tool that, let's post it in there again, Ava, that you can go use now. Do what a million users around the world have this model. And 850 of them have been well trained to do what this Hiska did in Amsterdam, to go engage with these questions using this model yourself, or in Kazakhstan, or in Italy, as they did in Italy, in Spain, in Boston. There's Kurt Newton, in the University of Missouri, in Germany with the maps, in India, in wherever this is, in the Netherlands, in Honduras. Be someone who engages other people, where you don't have to assert your findings, but engage people at a deeper level by showing them these scenarios and let them learn from themselves, no matter what their age is. Okay, I'm going to stick around. Go get them, everybody. Goodbye.